Take a standard food delivery app operating on a classic monolithic architecture. When a user places an order, a single centralized database handles the entire execution flow simultaneously. It creates the order record, processes the payment validation, and assigns a delivery driver in one continuous motion. Because this all happens in one place, it's safe. If any step in that sequence fails, the system triggers a standard ACID database rollback, cleanly erasing the entire transaction at the database level, as if it never happened. This diagram illustrates what happens when we shift that architecture. On the left, our reliable monolith. On the right, the system breaks apart into 3 distinct, independent microservices: order, payment, and delivery. Each of these new microservices now requires its own isolated database. That unified transaction boundary we relied on is permanently broken. Moving to microservices means sacrificing built-in database-level data consistency across the full user journey. Under normal conditions, the new architecture works fine. The order service creates the entry and passes an event forward to the payment service. The payment service receives the event, deducts funds, and rigidly commits the change to its isolated database. But notice the hard barrier. Suppose it's 4 a.m. The delivery service cannot assign a driver. Its local database transaction fails and rolls back. The architectural trap is that this local delivery failure cannot reach backwards through the network to trigger a database rollback in the payment service. The customer's money has been deducted, but no food will ever arrive. Distributed microservices cannot rely on native database rollbacks. Resolving this requires a new application-level approach to undo committed states. The industry-standard solution to this exact problem is the Saga Design Pattern. Saga chains together a sequence of local transactions. As each service successfully completes its step, it explicitly publishes an event to trigger the next service in line. To handle failures, Saga relies on a mechanism called compensating transactions. A compensating transaction is not a database rollback. It is a discrete, forward-moving piece of custom application logic explicitly written by developers to reverse a previous action. This visual maps out the failure flow. When the delivery service fails, it emits an event backwards through the chain, traversing the network to reach the payment node. This Spring Boot snippet shows the next step. The payment service catches the failure event and executes its compensating logic. It manually refunds the deducted money and updates its database state. Finally, the payment service finishes its compensation and emits another backward event to the order service, prompting it to run a cancellation routine. The Saga pattern replaces native database rollbacks with deliberate, programmatic undo workflow managed entirely at the application layer. There are 2 distinct ways to route these Saga events. The first is choreography, which is a strictly decentralized approach. This topology shows how choreography operates. Services communicate asynchronously by publishing events to a central message broker, like Kafka or RabbitMQ, without any central coordinator directing the traffic. Each service has localized autonomy. It listens for specific triggers from the broker, decides if it needs to act, executes its logic, and publishes a new event back to the broker upon completion. The primary advantage here is that there is no central controller. That means there is no single point of failure directing the whole flow. Independent microservices can be modified, scaled, or updated without bottlenecking a central authority. However, as more services and event steps are added to the system, the routing logic becomes incredibly difficult to conceptualize and track. You run into the specific risk of cyclic dependencies, where services inadvertently wait for or trigger each other in an infinite, unresolvable loop. Looking at this resulting web, tracking a single user's failed transaction across multiple independent service logs and writing integration tests for this becomes an operational nightmare. Choreography prioritizes system resilience and scalability at the severe cost of workflow visibility and debugging complexity. The alternative, Saga implementation, is orchestration, which brings centralized command back into the distributed system. This hub-and-spoke model introduces a dedicated Java component, the orchestrator, to dictate the entire workflow from above. The orchestrator functions as a state machine. It explicitly tells each participant exactly which local transaction to execute next. If the delivery step fails, the orchestrator instantly knows the exact state of the entire system. In this pseudocode state machine, we see how the failure flow executes. The orchestrator unilaterally and algorithmically issues the specific compensation commands without relying on individual services to guess what to do. This gives developers absolute visibility. You can track the entire transaction lifecycle, state, and fallback procedures in one single class or service. Cyclic dependencies are impossible when a single brain dictates flow, making integration testing straightforward, but it creates tight coupling. The orchestrator must intimately know the APIs and commands of every single participating service. This leads to the most severe architectural risk in this setup. The orchestrator becomes a single point of failure. Even if all independent microservices are perfectly healthy and online, if the orchestrator goes down, the entire transaction network paralyzes. Orchestration sacrifices system resilience and loose coupling in exchange for perfect visibility and simplified state management. Engineers must choose between choreography's decentralized autonomy and orchestration's centralized command. Choreography survives individual node failures, but heavily obscures the recovery path when things break. This comparison matrix highlights the trade-off. Orchestration provides a crystal-clear recovery path, but introduces a fatal central point of failure that can take down the whole system. The practitioner's heuristic is to use choreography for simple, short workflows with only a few participants, where high availability is paramount. Conversely, mandate orchestration for complex workflows where state tracking, auditability, and precise failure recovery are mission-critical. Ultimately, neither pattern gives back the effortless simplicity of monolithic AC database rollbacks. Moving to microservices means data consistency is no longer a free feature provided by the database tier. In distributed systems, data consistency is a complex, application-level responsibility that dictates the architecture and reliability of the entire system.